All right, so let's start off by looking at the homework. For homework, you had one problem, and I asked you to find a missing angle given two sides. So here we have that triangle. So we have our angle up here in the upper left corner, and we have the two values 8 and 6. Right, so again, obviously, the first thing you're going to do is you're going to label your sides. Right, so the 8 is across from the 90 degrees, so that is the hypotenuse. The 6 is touching our angle here. Oh, I wrote the wrong thing. So that is going to be our adjacent side, right? Because our angle is over here. So we have the hypotenuse and the adjacent. So for this, you should have used the cosine trig function. Right, so we have the cosine of theta equals the adjacent hypotenuse. If you're trying to make this a little quicker, you can write the equation of theta, right? So you can make theta equals, and then you would use the inverse cosine of your adjacent over hypotenuse. Right, so that's how it should have been set up, plugging in the numbers. Right, you can simplify this fraction if you'd like, but if you're just plugging it into the calculator, it doesn't really matter. It'll take, it'll give you the same answer either way. Right, here, again, we're talking about a triangle, so make sure we are in degree mode. Right, it says DEG. So I'm finding the inverse cosine of 6 over 8. And that is going to get us an angle of, we'll say, 41.4 degrees. So our theta equals 41.4 degrees. And there we have it. Any questions about that, about the homework? All right.
Easy.
What's up?
Said it's pretty easy. You taught it pretty well.
Thank you. I try. So do we have any other questions about inverse trig, setting it up, calculating it? I think we did a good job yesterday of going over it.
I think we're ready for the word problems, Mr. Murray.
All right, so let's start the word problems. I'll give you a second if you want to copy this down. That's a lot there. So just a word of advice. With these, I highly recommend you draw a diagram. Okay, this is an art class. I'm not asking for masterpieces. But I have yet to have a student who can visualize and set up the equations perfectly every time in their head. All right, there have been that have tried, and eventually, they mess up and the hypotenuse where the adjacent should be or whatever it may be. All right, so drawing a diagram solidifies what's going on, right? And you can visualize where everything is. So there are going to be a multitude of examples with trigonometry. All right, so we're going to deal with, how many you got here? Okay, I got 2 problems today, just dealing with basic, straightforward, triangles in real life. Tomorrow we're going to take it, like I said, I think I mentioned, into some physics stuff, and we're going to talk about harmonics and periodic motion and some other cool things. So we'll start off with just some basic triangle stuff, and then we'll expand on that. All right, so let me read this example, and then we'll tackle it. So we have a boat that is tied up to a dock with a rope. The tie-off point is 5 feet above the dock. Let theta be the angle of elevation, so vocab word from before, from the boat to the tie-off point, and let S be the length of the rope. Write theta as a function of S. So that's something we haven't really seen before, but I threw it into the homework problem there, so maybe you'll catch that. And then they ask us to find theta, right, in two different cases. So I'll give you another, I'll wait till that says 1040, and then we'll start to go over it. I'll give you some time if you're copying the problem down. All right. Let me make this diagram a little bigger. All right. So again, first you're going to draw a diagram. Now, if you don't want to draw a boat and a dock, right, just as long as you kind of get the concept, right? But I like being artistic, so I'm going to draw it. So we got our boat, little sailboat. All right, and then over here we'll have our dock. All right. Now, it doesn't really say it, but our boat and our dock are at the same level, right? So then you got some pole here, and then you got the rope tied to the pole. That pole is 5 feet. Now, let me ask you guys, the S, the length of the rope, would it go on this horizontal bottom line, or would it go on the diagonal line? What do you think? The length of the rope.
On the diagonal.
On the diagonal, right? Good. All right, so a lot of times you may have the procedures correct, but if you got that S down here, right, that's going to throw you off. Let me make that look like an S too. Let me make sure it's a 5. Okay. So then the other part is where the theta goes, and then theta is the angle of elevation from the boat to here. Right, so really the only angle of elevation that we see is this one over here. All right, so we have the basic part set up. We have our triangle. Now, if you wanted to be a little less fancy and just look at a triangle, right, that would be the same triangle, right, just without the illustrations. Okay, so the first part, they want us to write theta as a function of S. What that means is they want some equation as theta equals blah, right? So you may not be comfortable with coming up right away, but we know our basic trig functions where we can set up the initial steps, right? So with my angle being here, the S, the rope length is going to be my hypotenuse, and the height of the pole, the 5 feet, is going to be my opposite. So if I was just setting up a regular trig function, I would have that the sine of theta is equal to 5 over S. Now, this isn't a function of anything because we have, a function on this side and a function on that side. I gotta find a way to make my 5s not look like S's. Gotta practice. So they want the theta by itself. All right, so that's where we use our inverse trig. I want to move this sine over to the other side. So for the first part, theta as a function of s, that's what we have here. Theta is the inverse sine of 5 over s. Right. So that's it for part A. But they asked us to write an equation or a function, and that's what we have. Now they want us to find the actual angle when s is 40 and s is 20. Well, what's nice is we already have the equation set up. So this was A, this is B. So now we just got to plug it in. So we'll just go in order. So we'll do 40 first. All right, so we're going to calculate the inverse sine of 5 over 40. So we get a fairly small angle there. We'll say 7.2. degrees. Right, so when this is 40 feet long, we have a very small angle of 72 degrees. They also want us to find it, maybe we pull in the rope a little bit, we bring the boat closer to the dock, and now the rope is 20 feet. So let me ask you guys, before we do this, by making the hypotenuse shorter, do you think the angle is going to increase, or do you think it's going to decrease? If I pull this boat in to make the S shorter, right, the opposite staying 5, we can't change the size of the pole. Making this a smaller triangle, is that going to increase my angle, or is it going to decrease my angle?
Wouldn't it stay the same?
All right, so you think the angle would stay the same? That's a possibility.
Or
I want to say I agree
decrease?
with Barbara.
Okay, all right, so we got some.
Increase.
So we got a little bit of everything. All right, so let's take a look. Let's see what happens. So no, obviously there's a wrong answer, but we don't know yet, so let's find out. So we're going to insert the 20 instead of 40 there. So we're going to do the same thing. I'm just going to replace that 4 with a 2. And we get almost double the angle, 14.5 degrees. All right, so we actually, by decreasing that hypotenuse, all right, we're increasing the ratio, which increases the angle. So with that, so when we decrease this, we are also decreasing this side, right? So if I was talking about the cosine, if I was talking about the length from the boat to the dock in horizontal distance compared to the length of the rope, then there might not be much of a change as I increase or decrease the distance, right? My angle might not change. So if I was dealing with the cosine, we'd have a different story. The issue here is that this 5 stays 5, right? If the 5 also decreased with the 20, then the angles would more than likely stay the same, right? If everything was proportional. Because I can have 2 very different sized triangles, but if the proportions of the sides are the same, then my angles will still be the same. Okay, and actually you guys learned that back in geometry when you did dilations and similar triangles. Okay, they would be similar triangles if everything increased or decreased proportionally. All right. So any questions about that, setting it up and things like that?
We should do one.
We'll do one more. All right, so here we are now looking at a swimming pool. A swimming pool is 20 meters long. The bottom of the pool is slanted, right? So it's an in-ground where it gets deeper and deeper. It's 1.3 meters deep at one end and 4 meters deep at the other. Find the angle of depression of the bottom of the pool. All right, so this one I gave to you because, well, let's draw it out first and we'll see what's going on. So on one side of the pool, so here's my, pool deck or whatever. And so the first part of the pool goes down 1.3 meters, right? That's the shallow end. Then the bottom falls. And then on the other side, it's 4 meters deep, right? And then they also tell us that across, it's 20 meters across. So right now, I'm not really looking at a triangle. I'm looking at a trapezoid. So they want us to know the angle of depression of the bottom of the pool. Well, here, if I kind of try to find this angle, that would be an obtuse angle. That'd be greater than 90 degrees, which I want to set up a right triangle, so that angle's not going to work. So we have to do something to this to get a triangle, to get a right triangle. Well, this first 1.3 meters doesn't really matter because that's there the whole time. So what we can do is we can draw an invisible line. I'm going to make it dotted for now. A horizontal line that goes across, right? So sometimes we have to find the triangle in the problem. It's not always given to us straight away. All right, so here would be my right angle. This up here would be a rectangle that is 20 by 1.3. So I can bring this 20 here. Now, they don't tell us anything about this, right? So my hypotenuse, I don't know what the hypotenuse is. I can find it, but it's not really necessary. Now, the only issue, first, they want us to find the angle of depression. So now that we set up this triangle, we can see that over here, this would be my angle of depression. So I have the 20 here. I don't have a way of calculating the hypotenuse right now because I'm missing this side. Would this part here be 4 from there to there? Would that be 4 meters? Or how would I calculate that side of the triangle? How could I find that part?
Would you subtract 4 from 1.3?
You got it, right? So we already know that this part up here is 1.3. That's a 1.3. Right, so I would subtract those and I would get 2.7. Okay, very good. That's a decimal. Right, so just to make it look a little neater, I'm going to draw the triangle by itself. So we have 20 going across there. We have 2.3 over there. Obviously, it's not to scale. And then we have our angle of depression. Okay, so even though, they gave us this whole scenario, they didn't give us the triangle straight away. Sometimes we'll have to set it up to find that triangle. All right, so now that we got the triangle, we just go through our trig steps. So here's my angle. The 20 is the adjacent. The 2.3 is the opposite. So adjacent and opposite, we're going to use tangent. So we know that the tangent of our angle is going to be the proportion 2.3 over 20. So our angle is going to be the inverse tangent of 2.3 over 20. Right? So one other thing you can kind of think of, especially when we're dealing with tangent, it's a little more straightforward, is, well, obviously this isn't drawn to scale, but this 20 is a lot larger than the 2.3, right? So that means our angle should be pretty small compared to, everything else because we're not really increasing the vertical that much compared to the horizontal. All right, well, let's plug it in and let's see. Tangent, inverse tangent of 2.3 over 20. And we get an angle of depression of, we'll say, 6.6 degrees. And now, now that we have that angle, if they asked us for anything else about the triangle, we could figure it out. We could figure out the length of the bottom by using this angle or by using Pythagorean theorem. We could find this angle down here if they asked us to. Right? We can figure out the rest of the triangle, and that would be called solving the triangle. Ooh, for a second, I thought I didn't record. I scared myself, but we're good. All right, any questions?
No questions. None.
Okay. All right. So tonight I'll give you a problem like this. All right. It might be like a two-parter where I ask you to set up the equation. I don't know. We'll see how it goes. So keep an eye out for that. We'll go over it tomorrow, and then we'll continue with some different non-triangle examples. All right, guys. Have a good day. I'll see you all tomorrow.
Bye.
Bye. Have a nice
Bye.